is the following statement true, that A minus B unioned with A intersection B is just going to equal to our original set A? Well, let's have a look and draw this, right? Let's first draw the case where A and B share some elements together. Okay, what is A minus B going to be? Well, first let me label our sets A and B. A minus B is going to be every element in A that is not in B. So it means we want to highlight everything in A that is not also in B. So we are not highlighting this region because this region is in B. Fantastic. Then we want to look at A intersection with B. Well, that's going to be the region that has both A and B in it. So which region is shared by both A and B? It's going to be exactly this region. So we have one region and two regions, and we were asking for the union of them, so we want both of those regions. Well, what do both of those regions make? Well, it looks like it just creates the set A, which is exactly what we got on the right-hand side. Okay, what about if A and B don't share anything in common, right? They're two very distinct sets. Well, then A minus B is simply just going to be everything in A that is not in B, which is going to be all of A. And then A intersection B, well, there's nothing for us to shade in because A and B don't have an intersection anywhere. So we're just left with A unioned with nothing, which is just going to give us our original set A. So this is also going to be true for this case. Finally, if we look at the case where, for example, A might be a subset of B, what are we going to find? Well, A minus B is going to be everything in A that's not in B. Well, there's nothing for us to highlight here because if we highlight A, this part is in B. This part is in B, so we can't highlight anything. And then we want to also highlight A intersection with B. Well, where does A and B share something? Well, A and B both share this shaded region here. Okay, so we know this is going to be nothing, and that's going to be A. Well, A unioned with nothing is just going to give us A back, right? As per this image, we're just shading in the set A. Okay, one last thing we're going to want to look at is the other way around. What if B is a subset of A? Well, then we're going to get A minus B is going to be everything in A that's not in B, which is going to be this whole region here. And then we want to ask ourselves, okay, A intersection B is going to be the region that has both A and B in it. Well, which region has both A and B? Well, it's going to be this region here. Okay, so we're going to want to take this region, this huge region, and then this smaller region, and take both of them together. What do they make? Well, they just make our general set A. So I think it's pretty safe to say that this statement is going to be true, so let's go ahead and prove it. Okay, so in order to prove this statement, we have to recognize this is an equivalence statement, which means we have to prove everything on the left-hand side is going to be on the right-hand side, and everything on the right-hand side is going to be on the left-hand side. What do those two statements mean in math? Well, it means the left-hand side is a subset of the right-hand side, and the right-hand side is a subset of the left-hand side. Or, visually, it means this. We have left-hand side is a subset of the right-hand side, and the right-hand side is a subset of the left-hand side. And in order to prove this statement is true, we need to show that this is true and that this is true. And then we can conclude the statement is going to be true. So let's go ahead and do that. So to start this proof, we have to recognize this is a for all proof. The reason it's a for all proof is because this is for any set A and B. It's for all sets A and B, no matter how they're arranged, right? That's why I did so many examples. So that means we're going to start this proof with a let. We're going to say, let A and B be sets. Okay, now we'll get into our first case that we need to prove. Now let's prove the left-hand side is going to be a subset of the right-hand side. So for the first case, we need to show that every element in this set is going to also be in the set A. Or in other words, if we create some general element like X, which is going to represent every element here, or any element here, and we can then show X is also going to be an element of A, then because X represents any element in this set, and X is going to be in this set, we've shown that every element in this set is in this set, which makes this set a subset of this set, right? So how are we going to do this? Well, first let's figure out what it means for any element to be in this set. Well, it means that X is going to have to be an element of A minus B, or X is going to have to be an element of A intersection B. Okay, this gives us two cases we have to check. Well, this case has to get us to our goal, and this case has to get us to our goal. So what does it mean for X to be an element of A minus B? Well, this means X is going to be an element of A, and X is not going to be an element of B. Well, obviously, if X is an element of A and not B, X is clearly here an element of A. So we got the left-hand side to get to our goal equation, or our goal set, okay? What about the right-hand side? Well, for X to be in an element of A intersection B, it must be that X is an element of A and X is an element of B. Now in this case, x is clearly an element of A, so we can immediately conclude here that x is going to be an element of A. So there we go. We've drawn our sketch of our proof. So now let's put this into actual words and sentences. We're going to start by supposing our representative element x. We're going to say, suppose there exists some element x that is going to be in A minus B unioned with A intersection B. Fantastic. We're going to then say, then x must be an element of A minus B, or x must be an element of A intersection B. Great. Now let's do our first case, if x were in A minus B. So we say if x is an element of A minus B, then x is going to be an element of A, and x is not going to be an element of B, since, or I think that's kind of it. We'll just leave it at that, actually, I think. Yeah, I'll leave it at that. Then we say, if x is an element of A intersection B, then x is an element of A, and x is an element of B. And then we can say, in both circumstances, x is an element of A, so we can then conclude that this is going to be true. So because x is going to be an element of our goal set, it must mean that our original set is a subset of our goal set. So we're going to say A minus B unioned with A intersection B must be a subset of A. Okay, we've proven our first case. Let's go ahead and prove our second case. Okay, so for our second case, we're going to employ the same strategy as we did for our first case. We need to show that any element in A, we'll name it Y, must also be an element in our goal set, in this case, A minus B union A intersection B. So how are we going to do this? Well, it's difficult to break this apart. So maybe we should instead look at our goal and see, well, we can work backwards, right? Well, we can say, if Y is an element of A, then, well, we need Y to be here, or we need Y to be here. So we need to show Y can be in both of these. Okay, or at least one of them anyway. So we can say that, okay, well, if Y is an A, then Y is definitely going to be in A minus B, right? By definition of the difference. And then we can say, and, oh, no. From here, we can immediately go to here. And then separately, we can say Y is an element of A intersection B, which is going to make it an element of that. Yes, that should be fine, I think. I don't think we have to connect to these two. We'll just make them two separate things. Okay, let's give that a shot. So we'll start by supposing our element Y. We'll say, suppose there exists some Y in A, then Y in A means Y is an element of A minus B as well, making Y an element of A minus B unioned with anything, or in this case, A intersection B, as well as that Y being an element of A also means Y is an element of A intersection B. In fact, I think you can just leave it at this. You don't even have to prove the other side. As long as you can prove Y is in one of these, it'll always be in one of these, right? So you could actually theoretically just have proved this and then go immediately to your conclusion, but I'm going to be a little more thorough. I'm going to prove the other half as well. So we're going to say, as well as that, Y an element of A also means Y is an element of A intersection B, also making Y an element of A minus B unioned with A intersection B. Okay. Oh, actually, no. I made a mistake here. Okay. I have made a pretty big mistake. We can't say this. We can't say Y must be in this set because this means Y is in A and Y is in B, but we don't know that this is true. We have no idea of proving this is true. So we cannot say Y is going to be an element of this, because what if Y isn't an element of B, right? We have no way of knowing if Y is an element of B by just saying Y is an element of A. So the only way we can show this is from this pathway here. So in fact, we can't prove the other path. We can only prove y is going to be an element of A minus B, because we know y is not in B, because we didn't assume it, but we definitely know y is in A, which means y definitely has to be in this set. So there we go. We can now conclude what we were trying to prove, saying therefore A is a subset, maybe I'll write that a little nicer, A is a subset of A minus B all in a bracket unioned with A intersection B. Yeah, because we can't prove this by just saying y is in A, because we have no idea whether or not y is in B, right? We only know y is for sure in A. And which of these two conditions we definitely know y has to be in A? It's going to be this condition on the left-hand side. Okay. Now that we've proven both cases to be true, we can now write our conclusion. Our conclusion is going to be that since A minus B unioned with A intersection B, I forgot a bracket up there, is a subset of A, and A is a subset of A minus B unioned with A intersection B, then A minus B all in a bracket unioned with A intersection B must equal to A. So there we go, we've proven that this statement is in fact going to be true.